Swayam Prabha. Digital India. Educated India.
We had introduced this statement of first law, where we had said that the first law is coming because, or the way it was, the experiments were done was there was a gas in a container and there was a fan which was rotated, and the fan was doing work. And of course, that increases the pressure and temperature of the gas inside the container. So you cool down the gas, and so you know how much work has been done, how much heat has been removed in this entire cycle, and you bring it back to the original state uh, at which the gas was originally. And then you look at the work done and the heat transferred uh, in this entire cycle, and you found that the two things are equal. Okay? And this led us to the idea of something which is invariant of the path. So heat and work are both invariant of the path, but then we saw from very simple arguments that delta W, Q minus delta W is now going to be independent of the path. And therefore, this is going to be a property which is going to be represented as the total energy E. So these are the other alternate forms of the first law of thermodynamics that we had. The first equation, or if you integrate that, we have the second equation on this slide, um, which you can which you can see here. Now we said that the total energy comprises of several components. It has the internal energy, which is essentially the energy of the molecules. And then we have the kinetic and the potential energy of the entire system. And therefore, we can write the total energy as internal energy plus kinetic energy plus potential energy. And of course, each of these energy components are, again, point functions. And therefore, I mean, we can write it out in this form here. And of course, because internal energy is also a property, although it's an extensive property, so we can define an intensive property by dividing it by mass. And then we can use this internal energy, specific internal energy, as a property to define the state of a pure substance. Then we moved ahead and defined the idea of enthalpy, where we said that we are now going to combine certain properties. Here, we are combining U and PV, and we are getting a new, because each of these are properties, the combination is also a property, and we're defining it as an enthalpy capital H, and per unit mass basis, we're defining it as a small h is equal to small u plus p times a small v. And of course, enthalpy was introduced in the context of a gas which is heated from one side and which has a piston on the other side, or the cylinder has a piston on the other side, and therefore the piston moves and does work against the surroundings. So we could write the total amount of heat which is being supplied using our first law as the difference in the internal energy and the amount of work that is being done, which is of course P times V2 minus V1. It's a constant pressure process. But then we said that this whole idea of enthalpy, I mean, of course, then we can see this naturally combination of U plus PV coming out. But we said that this combination is not going to be limited to only this specific example or problem or case, but it is going to be applicable in general. And the basic idea is that the enthalpy the internal energy shows up when it's a fixed system, whereas when you're going for something which has a moving boundary, or there is some work which is being done, or then it's an open system where we'll see that work is done, then enthalpy essentially gets involved. Then we said that we can define further the Cp and Cv. These are also two important functions, thermodynamic, for calculations of various properties, especially for gases. And of course, again, we can emphasize that Cp and Cv are again properties which can be used to define the state of the gas if required. Now, the next thing, of course, the definition of Cp and Cv, you know, but what we want to now show through an argument, through like an experiment which was done, is to show that internal energy of an ideal gas is a function of temperature only. Now, for this, what we will do is assume that there are two tanks, A and B. One of them has a gas which has at certain pressure, whereas the other tank B is at vacuum. So initially they are isolated because there is a valve which is closed and the gas cannot move from one cylinder to the other. But now what we do is, of course, at some time t is equal to 0, we open the valve, and of course the gas will go from the tank A to tank B. Of course, thereby reducing the pressure of gas in tank A and of course increasing it in the other side. Now, what was found is the temperature of the gas in A does not change. So that means that there is no amount of heat transfer that has happened in this case. And of course, this is also gas which is expanding in vacuum. So there is no force which this gas is. It's just a free expansion. The molecules are free to just expand. And of course, we are assuming it's an ideal gas. So there is no intermolecular forces as well. So there is no work that is required to be done anywhere because there is no force which is involved anywhere. So we find that there is no heat transfer which is happening. There is no work which is being done. And therefore, the internal energy of the gas A cannot change. So this is a simple argument. And here, what is coming from this experiment is that there was no change in the temperature that was found. So this is the basic observation. The last point in this slide here is a basic observation that was made, because this is clearly stating that there is no heat transfer which is happening. Other points we can argue. Okay, therefore, we can see that the internal energy of the gas A cannot change because there is no heat transfer or there is no work which is involved, although there is a change in the pressure and specific volume of this gas A in the container A. Okay, therefore we can conclude that internal energy is of an ideal gas is not a function of pressure and specific volume, and it only depends on temperature. So this is the argument which was used to show, or this was an experiment which was used to show that internal energy of a gas is only a function of temperature and independent of pressure and specific volume. Any questions here? Okay. So moving ahead. So for an ideal gas, this is essentially what we are writing. Okay, because it is no longer, earlier we had said, so here it's only a function of temperature, so we can write du as a total derivative now, instead of having a partial derivative, because we have already shown that it is only a function of temperature and not other quantities. So we have changed the partial derivative to a total derivative here. And of course, and because we know that H is equal to U plus PV, and for an ideal gas, PV is nothing but RT. So therefore, we can see that, you can see that, of course, U is only a function of T, and of course, this is just a function of T. So you can see that H is also now only a function of T. Okay, so which allows us again to write a similar sort of an expression with total derivatives for Cp. Of course, Cp0 and Cv0 are functions of temperature only. And of course, if you would like to see how these are varying for various gases, this is over a reasonably large range of temperature. Cv has been plotted here. So you can see up almost from 250 degrees Celsius to almost like 1800 or 2000 Kelvin. So over a reasonably large range of temperature, this is how the values of Cv varies for various gases as given here. Now, As a further reduction, what we can say that dH is equal to du plus r dt, and we get an expression which has been given here, and therefore, of course, dt we can cancel out from both the sides, and we get that r is equal to cv p0 minus cv0. So essentially, it means that irrespective of how cp0 and cv0, both of them are functions of temperature, but the difference is going to be a constant, or that means independent of everything else. And of course, it also means that because u is a function of t and nothing else, and similarly, we have shown that h is a function of t and nothing else, therefore, lines of constant temperature are also lines of constant internal energy and enthalpy. So this is also all of them are essentially coming from the deduction. I mean, these we can simply deduce from the observation, and we are essentially writing out all these points explicitly so that we can use them for further calculations and so on. And therefore, we can say that if we are going from one line of constant temperature to another line of constant temperature, okay, irrespective of again the path that has been changed, okay, the same amount of internal energy is going to be involved. Okay, so any two points on these two lines we can take, and we can move from this, I mean, any from one line to the other line is essentially what we are saying, and irrespective of how we are going, irrespective of the points that we have chosen on this line, we are always going to have the same internal energy. And of course, it is coming from this reduction is coming from the previous point. And of course, this reduction is coming from the experiments that we have done. Okay, any
Excuse
questions?
me, sir. Excuse me, sir.
Yeah, please go ahead.
Sir, what does the subscript 0 mean here? CP0 and CV0?
It's just that it is defined at some reference temperature. Okay,
Okay, okay, sir.
so it has not too much of a significance here. Anything else? So this is pretty straightforward, I believe. Now, if you have to sort of generalize this to solids and liquids, then all you need is essentially what is shown here in this slide. So for solids and liquids are essentially incompressible. And of course, incompressible means that the specific volume or the density is constant. Therefore, the dH, I mean, from H is equal to U plus PV, if you want to take a derivative of that or differential of H, you can write it in this form here, where we have removed the other term. Of course, you should have a second term, a last term, which would be in this equation here. We should have a PdV term because we are saying that V is essentially not changing. So the PdV term has been removed, and we have changed from the equality to an approximation. And further, because from the steam tables again and from other tables that you would see, and of course, this is something that we know, that liquids and solids have large density. Therefore, their specific volume is small. Of course, uh, large and small is always relative. So we'll have to see with respect to what. But so here we are assuming that with respect to the other terms, this term VDP term is essentially small, and the argument is because, or it becomes small because essentially our V typically is small, and therefore we can get rid of this last term as well and show and argue that dH is approximately equal to du, and of course which is essentially C dt now. So we had said that du essentially becomes Cv dt and dH becomes Cp dt. Okay, that's what we had seen for gases, but because here dH is essentially equal to du, so that means that Cp and Cv are essentially the same. Okay, so that's the point that has been given here, and we are now no longer need a subscript. Okay, so we are just calling it a C, and of course C you can think of that either it's a constant volume or a constant pressure, specific heat, it does not matter because both of them for solids and liquids. As per this argument, of course there are approximations here, but because these approximations are deemed to be good, we can essentially write an expression like what has been given here. And of course, from here we can simply say that If we were to integrate this equation, this is what you would get. Okay, any questions here?
So,
Please go ahead. Yeah.
so we derived the result that du will be equal to CdT only for ideal gases. Then how are we using it for solids and liquids? That internal energy is dependent on temperature only. We derive that result only for ideal gases. Then how can we use it for solids and liquids as well?
Yeah, actually, that's a very good question. So we have not explicitly shown that the for other solids and liquids. So we are sort of saying that the same sort of concept or idea would apply. See, anyway, in a solid, for example, if you change the pressure, do you really change? Think the energy, internal energy of the solid would change? So there it is much more, I mean, sort of intuitive to see that the internal energy of the solid is not going to be pressure dependent on the, the pressure that you are applying, right? So, I mean, and of course, the same thing we can argue for specific volume. So one can sort of see quite readily in that sense that is only going to be a function of temperature, and therefore we can deduce or write the way we are writing here. Okay, does that answer your question?
Okay, sir. Sir, but by applying pressure, we can deform the solid. So we can, I don't know I'm saying it correct or not, but we can change the state of a solid by applying pressure. Does that change the internal energy? I don't know.
I don't know. I mean, I don't know whether the statement, first of all, is correct. Of course, if you are thinking of very, very large pressures, then it's a different story. Okay. And then, of course, the other thing that we have to look at is these are approximations. And we are very clear in stating that these are approximations. And these are going to be applicable for the conditions for not the extreme cases that you are talking about. So we can sort of qualify, if you want, by saying further that typically this is what happens. So we are not looking at extreme cases. Of course, if we are not, then of course some of these approximations may not apply, and what you are saying rather would hold.
Okay, sir. All right. Thanks.
So again, it's not that we so these approximations we are making so for convenience, okay? Because most of the time this applies, but of course we are not stating it as a rule. These are not rules. So in some sense you are right. So we are not contradicting what you are saying, but we would still like to go ahead with what we have said because of the fact that these are all, I mean, typically applicable and therefore useful to know. Okay.
Okay, sir.
So now what we will do is, of course, this is a simple, if you want to write it as a rate equation, just for the sake of completeness, I have written this here. Okay, so sometimes you write it as per unit time, things, how things are changing. So you can write it out, the first law in this form. Now what we will do is we'll take one example. So what I'm realizing is based on the experience of uh, the tutorial last time is that it is sort of going to be difficult to answer each question individually. So what I'm trying to incorporate here is that I'm going to show you some typical examples where I have seen from the experience from the previous batches that people have difficulties on certain ideas and concepts. So I'm going to solve them. I'm basically bringing them as a solved example. Okay, and I'm giving you tutorial sheets. The tutorial sheets, hopefully after this, you should not have any difficulties. So tutorial sheets is essentially up to you to go back and solve. We would expect you to solve, okay? But I mean that's up to you. If you solve it, it will be good for you. And hopefully you will not have any difficulties because not just the main ideas have been covered in the lecture, but some of these typical issues are being pointed out through these examples here. Okay, so I'm trying out this model. You can give me feedback on this model. So hopefully, so again, what we are saying is we will try to cut down on our tutorials. We'll keep giving you tutorial sheets, but then to supplement that, we will give you solved examples. We will have solved examples, one. And of course, you are free to contact us individually. So we can solve individual examples, individual problems. And if we find again that there are certain commonalities where a lot of people are having difficulties, then we will come back to the class and solve it for everybody. Okay. So this is the sort of proposal, or this is the model that I'm going to operate. And you can give me feedback on what you think about it. So this is one example where we are saying that, let us say that there is a vessel which has 5 meter cubed. And of course, I'm just solving it. I have solved it and I'm going to bring out the important steps here. And again, it is important that you go back problem on your own, maybe just close. I mean, just look at this problem statement and try to solve this problem. And then of course, you can check what I have done. And of course, just like last time I had made a typographical error, if I have made a mistake, you please point it out. So hopefully it will be error free, hopefully. So basically what has been given here is a vessel which has certain amount of liquid water and certain amount of water vapor, and the pressure has been given to you. And all it is saying is that the vessel is heated till this entire vessel is filled with saturated vapor. So what is the first thing that you can deduce is that because both liquid and vapor are present, okay, this is in the saturated region to begin with. That's the first thing that should automatically come to you. And then we are now heating it up, and we're heating such that all this liquid water evaporates and all we are left with is saturated vapor. Now the other thing which is there is that this is a vessel. There is no piston or anything. So you can assume that this vessel volume is not going to change. You can also assume, and of course this is not really an assumption, this is sort of given already in some sense, that the mass which is inside this is not going to change. The amount of liquid water plus amount of water vapor, the amount of water content that you have inside this vessel is not going to change with the heat amount of heating. So these two things is a constant volume and the constant mass, which is also there for you. And of course, that should tell you that the specific volume for the system, that means it's not changing. Okay, and this is one point where I had a lot of difficulty from the previous batches. I'm bringing it out here. Okay, so your vessel is fixed. So fixed walls, so volume is not changing. The amount of mass which is there inside is not changing. So that means your specific volume, which is total mass, total volume divided by total mass, is not changing. Of course, the first thing when you look at the statement, you try to have a figure. Okay, whether you plot it out or not is up to you, but I would always suggest that you have a figure. So what happens is when we grade it, we are also clear that you understand what is the problem. Okay, it becomes easier for us. Okay, so this is the first state, and then you have gotten to the second state where you have now changed everything to vapor. The next thing is to have a appropriate figure, like a TV, PV, TPT, whatever diagram, or a TS, etc. You can have one of these figures and then try to find out what are the states which are there and how you are moving. Okay, so if you do that, it becomes again very easy for you to understand. You have clarity as to what is happening before you try to attempt it, and we know that you understand what is happening. So as we said that if you look at it on a TV diagram, okay, you start off in the saturated region. This is somewhere at your point 1, and then you're heating it till it is filled with saturated vapor. So you're not going into the superheated region here. So you stop the amount of heating at this point 2. So the next thing that you have done after drawing this figure is to be able to see how things are moving, or we are trying to locate these various states which this water is undergoing. Now, what is required is the amount of heat which has been transferred. So what we want is essentially U2 minus U1. And now why U? Because again, it's a fixed mass system, and therefore the internal energies is what we are looking at.
Sir, can you please repeat how we located state 2 in this diagram?
We have not yet talked about that. So what we have said is that we are moving vertically. Why we are moving vertically is because we are not changing V. Okay, so V is fixed. That's one thing that we have said. Now, the other thing we have said is that we are going to stop when we get saturated vapor. So this is saturated vapor. This solid black line curve that you see here is quality. Of course, on this side, it is quality 0. On this side, it is quality 1. Okay, so this is quality 1, which is saturated vapor. And you are not going to heat it further and go into the superheated region. Okay, because you are filled with saturated vapor. Okay, after that, it will become superheated vapor. Okay, and it's not somewhere in between also. Okay, because in between you have both liquid and vapor. So it is not just saturated vapor. Okay, so it is not before and it is not after. It is at this point here at x is equal to 1. So essentially looking at the intersection of these 2 points, keeping constant v, drawing a vertical line, and your point of interest is when it intersects this curve, black curve here. Does that answer your question?
Yes, sir.
And now what we're interested in is U2 minus U1. So what we will do is first find U1, and of course then we'll have to find U2. So at 1, what do? I know what is the pressure level I'm operating at. Okay, this is the pressure. It has been given as 0.2 megapascals. And remember that 1 megapascal is 10 to the power of 6 pascals. And of course, 1 bar is 10 to the power of 5 pascals. So then 1 megapascal is like 10 bars. So this is 2 bar pressure on which you are operating. So at 2 bars, I can find out what is my VF and what is my VG. Okay, so I go to a steam table, look at 2 bar, okay, and I should be able to find out all these 4 numbers, VF, VG, as well as UF and UG. Okay, in fact, if you want, I should have this. You're going at 2 bars, 2 bar pressure, and you are essentially reading, this is your VF, VG, and similarly you are reading UF and UG. Okay, UF and UG. Now, the next thing that you'll have to do is to find out how much vapor is there. Okay, so your vapor is of course Vg upon Vg, capital Vg upon Vg. So you know that it is, to begin with, it was 4.9 meter cubed of water vapor. And you have figured out what is my small Vg. So you can find out what is the mass of vapor that you have. Similarly, you can find out what is the mass of liquid which we have. And you can find out, now you can find out what is the amount of energy that is there in your vapor, in your vapor here, which is mgug. Okay, mass of the vapor multiplied by the specific internal energy will give you the total internal energy that is contained in my vapor. And similarly, the same thing I can do and find out what is the internal energy that is contained in my liquid. And of course, the total of these two will give me the total internal energy that I have in my system to begin with. Okay, so put all these numbers, you get certain amount of internal energy. So you have essentially now found U1. Now you have to find your point 2. So first you have to find out, so we said that it's a vertical line, so we'll have to find out what is my V2. Okay, we know V2 is essentially V1. This is one information that you have. And now again, I'm repeating myself here. V is the same because it's a rigid container. So my volume is not changing. And of course, the mass which is contained is not changing. So my total volume by total mass is not changing. So now I know how much total volume has been given to me. Masses I have found out. So my total mass, so I can find out what is my V1, and of course that's the same as V2. And we've already said that X2 is 1. So this, we have 2 properties now, and therefore I can find out what is the state 2. So what do I do now? So I am now going to look at what I'm going to do now. Let me just, can somebody, so this is my steam table. I have found my V as 0.05. 0.01, 0.05 we have found. Now what will I look for?
We will look for values for the saturated vapor Vg between which this value lies.
Very nice. So we will look at the value of Vg, which is between 0.05. Okay, so in fact, I had initially made a mistake here. I was thinking this value, but it is 0.05. We have to go to somewhere here. Okay, so it is essentially lying between these two numbers. Okay, so I'm looking at the value of Vg. This is saturated vapor. I know there is no liquid. It is saturated vapor. And at 35 bars, I will have a specific volume of 0.057. And of course, at 40 bars, I will have this 0.049578. And my value lies in between. So I'm going to now linearly interpolate between these two, between 35 and 40 bars, and I get my pressure, and I can also find my internal energy. Okay, of course, for internal energy, I'm now going to look at only your UG at these two levels. So UG at these two levels I have taken, and I have used the interpolation now because I know what is the volume I need to have. So essentially this ratio turns out to be something like 0.956. Okay, and I mean, these are linear interpolation. I'm sure you can do that. And anyway, hopefully the worked out example is already given. So hopefully there is no mistake here. So from here you can find out my U2, and therefore heat to be supplied is, of course, this is the equation that we are using now. This is coming from the first law of thermodynamics. Here it is very clear that there is no amount of work which is done. There is no moving thing here. There is no shaft. Okay, so there is no work which is involved. Okay, we are assuming that there is no change in the potential energy or the kinetic energy. And these are reasonably good assumptions because we are not changing either the height of this container or we are not moving it at a different velocity here. So therefore there is no change in the kinetic energy and the potential energy. So we are essentially left with U2 minus U1. Okay, so the required amount of heat is essentially these things here. So again, let me just emphasize a few things here. Okay, it is good. So if you, here I have not tried to take any shortcuts. So you can refer back to this example, okay, as to how I would expect you to do the problems here. So what we are doing here is stating explicitly that there is no change in the kinetic energy and the potential energy. Okay, there is, in fact, I should have stated explicitly that there is no work. Okay, so it is very, you should state these statements very clearly. Okay, you can see that the units have been put everywhere. Okay, so the units are also cancel out as we go along, or they get carried forward, whatever. So the point is that you have to be careful and try to do things carefully enough so that the entire working is very clear. Okay, with the help of figures, etc., and very clearly stating how you are moving from one point and to on and so on. So any questions here?
Sir, can we use enthalpy difference for this question, assuming that there is no change in the kinetic energy and potential energy from the table?
Yeah, so you can try doing that, but of course that does not make sense. Okay, because again, there is no PV work here. Okay, so there is no PV here, so it does not make sense. So enthalpies is not the right thing to look for. So again, we have tried to say very clearly that internal energy, change in internal energy is what gets involved. And of course, it is clear from this example here, right? This equation, this entire equation is right here with you, before you. Okay, so this is the equation that I am applying. And what you see is essentially U2 minus U1 gets involved. So where do I see H2 minus H1? I don't see that. How do I get H2 minus H1? H2 minus H1 was only coming if we are saying that this work is essentially PV. Okay, essentially it's P2V2 minus P1V1. Then of course the enthalpy is H2 minus H1 will get involved. But I don't have this term at all. So then therefore writing it out as H2 minus H1 is incorrect. Answer may still turn out to be very close. Okay, but the idea is that the idea is incorrect. So yeah, so this is an important point. In some sense, you can say that my answer is still very close, but in this case, you will be have to be marked. We'll have to. I mean, we'll have to. I mean, we will say that you have not understood the problem. Okay, because you are not using the right quantity. Okay, so somebody may have a very different answer to this, although the concept may be right because there is a calculation mistake. So that person will get more marks than you using H2 minus H1 because H2 minus H1 is incorrect. Although you may be closer to the final answer still.
Excuse me, sir.
Yes.
Sir, in the case of work done, which is integral of PdV, and if I have P as a function of V, then it is not essentially P2V2 minus P1 V1, the work done. So
Yes.
in that case, can I use enthalpy to calculate the heat transfer, or do I have to explicitly calculate the work done using integration?
Yeah. So I will go back to the slide on enthalpy and say that this is a special case. Okay, so here the work done in this case was turning out as P times V2 minus V1 because we are assuming that it's a constant pressure which is acting on this gas here. So pressure is not changing. Okay, and of course we can therefore we can P2 is equal to P1 is equal to P, and therefore we are writing it out in this form here. Okay, so we said that in this case H is equal to U plus PV, but this is not going to be limited, and internal energy is going to be involved. Okay, and of course, see, if you don't like it, you can always go back to the first law, the way we have done it, this solid example, and you would be able to see very clearly what is involved. Okay, just write out each of these terms and you would know. Okay, and once you start getting a hang of what gets involved, this is the statement, you will start seeing the validity of the statement then. And before we move ahead to to the first law for a control volume next, that's what we'll take next. Continue the lecture here. So basically now what we will do is apply the first law of thermodynamics for a control volume. And so till now we have been essentially looking at the first law for a fixed mass. And here we will do it for a control volume where we would allow for mass to enter and leave the control volume. Now when we do that, earlier we were only looking at energy, but now we have to look at conservation of mass first and then conservation of energy. So both these two things have to be explicitly, we have to write explicit equations for conservation of mass and energy because we are allowing mass to come in and go out. So is my mass still conserved? We don't know. So we'll have to write out a separate equation for conservation of mass and a separate equation for conservation of energy before, uh, I mean, both these two laws have to be applied. And typically we apply the law of conservation of mass first. This is a practical, from a practical point of view, because you have both the laws before you. Which one should I apply first? So to answer that, I'm just stating that the law of conservation of mass is almost always applied before the law of conservation of energy. Again, can you see my slide?
Yes, sir.
Thanks. So this is a general idea that I'm starting off with. And once we understand this idea and how we are going to write things further, and let me tell you that this idea is not just limited to what we are doing here, but you will see that the same idea essentially is applied in fluid mechanics and heat transfer as well. So this is a very important and a general principle that has been given here. And maybe to motivate that, so there are certain terms, accumulation, growth, influx, and efflux, which has been given here. Now to motivate that, let us just think of, let us go to a practical problem and see how we would do things there and then come back to what I've written to this slide, and hopefully it will make much more sense that way. So this is my favorite example, and I'm sure some of you would have heard this. So basically the idea is that we are wanting to count the number of people which are there in a village. Okay, so we want to know how many people are there in a village. Okay, so that's the basic problem that we're looking at. And we know that, so the first thing that we will do is we want to do that. So we know that the would change the number is of course births and deaths. Okay, we also know that there can be people coming into the village and people can leave the village. Okay, so you know that this is now no longer a straightforward problem because of all these events that can happen. So the first thing that I'm going to do is to draw a boundary. I will say that this is my region. Inside this region, I'm counting the number of people. So that's the first thing that I do. And if you now want to look at the equivalent of that, so the equivalent of that is this control volume that I'm having. So this I have to first define my region, of course. So the region is defined, which is defined by this control volume. Now, so So what we are looking at in some sense, now if I go from my example to what is given on my slide, I'm looking at the change in the quantity of interest in my control volume. Here in the example, there's the number of people which are there in the village. So this is the quantity of interest is my number of people. And otherwise, this is any accumulation, any change in this number is what I'm looking at. This change in number that I'm looking at of people can happen because of birth and deaths. So of the people inside this village. So this is like a growth term. I'm calling that as a growth term. And then I can have people coming in and people going out. So this is my like an influx term. Okay. And there is an efflux term. Okay. So the number can change. So now so we are now saying that there is something, the mass can enter this control volume. And this is now going to be counted only at the boundary. So from the boundary, if somebody crosses it, I will delete that number, that person's name from the list. And if somebody comes across this, then I will add that person. So these terms are happening, influx and efflux are happening at the boundary. They're not happening everywhere. So people moving inside this control volume, I'm not bothered. I'm only going to be bothered about somebody who's going to cross this boundary, the imaginary boundary that I have drawn. So that means that it's like a control surface, which some mass which is crossing that, then it becomes relevant. These terms become relevant for us. Now, when the mass comes in, they bring in along with itself, they're bringing in like momentum, they're bringing in energy, they're bringing any other quantity. So the incoming mass is essentially bringing, so in this slide, what we have said is that the incoming mass is bringing the quantity of interest with itself. And similarly, when mass leaves, then it is carrying away the quantity of interest with itself. So these two things have to be appropriately accounted for. So just like in this village, this is all that can happen. Births and deaths are taken care of this in this growth term. Okay. And all this births and deaths and incoming and outgoing people can change the quantity, the number of people in this village. And so therefore, we are saying that we are calling that the change in the number is accumulation. Of course, accumulation means that people can increase this in this control volume in the village. And of course, it also has, although we are calling it as a growth could be positive or negative, again, depending on whether it's a birth or death. Okay, and accumulation, of course, it can be positive accumulation and negative accumulation. So the sign is automatically implied here. I mean, so it's just an accumulation. We're just calling it as a general term, accumulation. It can, of course, be either positive or negative. So is this general idea clear? And of course, so that is what, so from this example, you can see how we are writing this general physical principle. Okay, so in physical principle, the language we are using is accumulation is growth plus influx minus efflux. And hopefully from this example, you will understand what we mean by growth, what we mean by influx and outflux. And of course, we know that what we mean by accumulation. Okay, is this clear? I will pause here and wait for questions. Because this, as we said, is a very important physical principle based on which all laws in fluid mechanics, heat transfer, thermo, etc., everything is being derived. So this is the basic idea. Okay. So we are now going to use this physical principle to drive the equation of conservation of mass and equation of conservation of energy. And we don't have time today, so we will not get into this. We will leave it here and think about this idea, about this general physical principle that has been given here, based on which we are going to drive our conservation of mass and conservation of energy. Because once the statement is understood, okay, it's a matter of applying each of these terms for the context that we are interested in. Okay, and hopefully that will not be very difficult. Okay, so we'll pause. Any questions here on anything that we have covered in today's lecture?
Sir, I had a doubt about the compressibility factor part that we had covered like in earlier lectures.
Yes, please.
So, if we want to find the compressibility factor, we divide the actual volume by um, the the ideal gas volume, which would have been.
Yes,
But
yes.
if the gas is in a fixed container,
Mm-hmm.
then like which one is the gas will occupy the whole volume of the container. So the actual volume is the volume of the container. Then what? How do we find the ideal gas volume?
If you take the gas, same gas, and put it in a bigger container, it will have a lower pressure or temperature may also change, right? So they are
Yes,
all
sir.
different. So basically, what we are saying is what is the actual for a given pressure and a given temperature. So that's why now we are saying for a given pressure and a given temperature, what is the actual volume that the gas is occupying? Okay, and
But
divided by what is the volume as per the ideal gas law that it would have occupied. And the ratio of these two is my compressibility factor.
if we are given the volume of the container, then won't the actual volume just be that value of the
But then,
volume of the?
yeah, so that is right. But then your pressure has changed, for example. The temperature may also change, but let us say that only the pressure has changed. So now so the actual volume is what we are saying is the volume of the container, but then you go to an ideal gas law, put the actual value of pressure that you are now having, okay, and the actual temperature that you are having, and based on the ideal gas law, find the volume that the ideal gas law would predict. Okay, so that's
Okay,
the
sir.
volume that you're getting from the ideal gas law. And you look at what is the actual volume that the gas is occupying. Okay, so now you have actual volume, you have actual pressure, you have actual temperature. So actual volume is actual volume, but you use your actual pressure and actual temperature in your ideal gas law to predict the volume which is predicted by the ideal gas law. Okay, and then you take the ratio of the two volumes.
Got it, sir. Thank you.
Okay, so people can are free to sign off.